Good evening. Welcome to tonight's Science and Cocktails session. The Science and Cocktails, for the ones who do not know, is a joint corporation between the Niels Bohr Institute and Bundsluis, this magnificent theater. Its objective is basically to bring science closer to people in a very relaxed environment, because science normally only reaches people through the media, and in most cases distorted. So in this event tries to bring everyone who wants to know about science in contact with the scientist himself, and where you can approach him at the bar, ask him questions, buy him cocktails, whatever you want. So tonight we have a very special guest. His name is Eugene Polzik. He's a professor at the Niels Bohr Institute. He's the head of the quantum optics group. And his research, at least recently, has been so far concerned with quantum teleportation. He has recently been awarded a very prestigious grant of 35 million kroner. So he's totally loaded with money for boosting up the quantum optics group at the Niels Bohr Institute. So he was telling me just before that people would have to buy him cocktails to ask him the questions, whatever. But I think it has to be exactly the other way around, because he has trillions of money in his pocket. So, okay. Afterwards, we'll have just a 5-minute break, and you can approach Eugene at the bar as much as you want and ask him the questions you want. And as that goes on, Cecile Svensson, she's a singer-songwriter. She's very creative. Her songs are really beautiful. So you should stick around and give a chance to listen to this amazing music. So I hope you enjoy, and let's applaud Eugene. Yeah.
Am I on? Yep. So, yeah. I'm sorry I only have 45 minutes. My Bentley and my chauffeur are waiting outside, so we've got to be quick. Despite that, it's going to be confusing. And it's not because I'm bad or you don't have enough background, but because quantum mechanics is confusing, period. And there was a famous statement by Richard Feynman, who would say to those students who would come to him and ask, you know, what does this all mean? He would say, shut up and calculate. And since I'm an experimental physicist, I say to my students, shut up and go and measure. So let's try to get as far as we can with the presumption that quantum teleportation sounds much sexier than it actually is. And the 6 people who invented the idea, it was 25 years ago. They just had a good time, and they liked Star Trek, and they thought, why don't we call this thing quantum teleportation? So let's just see what happens. Those are 2 guys, Pauli and Bohr, and they are looking at something which is a topspin. And this topspin looks a little bit like an electron rotating around the atom. And the electron rotating around the atom has a magnetic field, a magnetic moment, which I will call today a spin. So you better get ready to the word spin. So spin is a little magnet. And well, I just make a little advertisement for our center. Lots of those transparencies are actually recycled from the real scientific presentations, so I'm sorry. But this young man by the name Werner Heisenberg was a guest of Niels Bohr here in Copenhagen some years ago, and allegedly here he thought of one of the ideas that actually turned our feeling of the world upside down, and that was the uncertainty principle. And the uncertainty principle tells you that you cannot, you, I, whoever, we are not allowed to learn everything about the world that surrounds us, which is kind of good news, I think. otherwise it will be too boring. So what is it that we cannot learn? For instance, if we take, well, a little, so you see, good students who sit in the front row always get a better view, right? So if we have, you know, an atom and there are electrons running around, we all know that we are built of molecules, atoms, there are electrons running around. We are not allowed to know the position and the velocity of those electrons at the same time. Either you can measure exactly where this electron is, or you can know how fast it goes. And not altogether. Which means that if you have this particle, a little electron, and it moves, you cannot predict the trajectory. So if you know where it is, you don't know where it's going. If you know where it's going, you don't know where it is. And this is how the world is about us. Well, that means that we cannot predict the future, even in principle, right? If we cannot predict the trajectory of a single particle. So, in my view, also good news. But the point is simply that there are complementary, what we call observables. In this case, a position and the velocity of a particle, which we are not allowed to measure. And there is more than one example of such things. And for those of you who happen to have quantum mechanics in your childhood, those are called non-commuting operators. So the position and the momentum, which is the mass times velocity, they're non-commuting operators. Sounds fancy. And this little thing is called the Planck Constant. It's good, you know, it's good to know such names, right? Like when you go to the bar and you speak to your friend, you say, do you know what the Planck Constant is? So, may be useful. So, long story short, the teleportation is about transmitting something that you don't know and you cannot, in principle, learn. I repeat, this is important. The teleportation is a process of transmitting something that nobody can know. And yet, you can transmit this thing, this information, from one place to another. And this is remarkable. This is much more remarkable than beam maps, Scotty, in my opinion. So, the first wave of quantum mechanics started in this very city by Niels Bohr and by people who came to visit him. And because of this wave of quantum mechanics, I can speak to you through those microphones, you can search your internet, you can listen to your DVDs, you can fly those jets and whatnot. You can use the camera. It's all because we invented quantum mechanics, the mankind. And we learned how to do semiconductors and stuff. And this whole wonder lasted for 70 plus years. And in fact, there are anecdotes that the giants of the 20s, of the 30s, like Niels Bohr and Heisenberg and de Broglie and whatnot, they seriously thought that everything is known about atoms and light. Just, you know, don't worry about it. Let's go to something more complex. Let's go to chemistry. Let's explain biology. And then all of a sudden, the second revolution struck. And that was not long ago. And then we rediscovered things. We rediscovered quantum mechanics and its connection to the science of information. So it turns out that physics and information are intimately connected. So let's see how it works. So there are quantum objects around us, those little electrons. We are quantum objects, except for we rarely behave like such. Mostly we behave like predictable classical objects, simply because we're big and bulky. And it's really difficult to find the quantum features in us. Although if you look carefully, you might. The quantum objects, like I told you, they cannot be measured. I cannot measure the position and the momentum of the electron. They cannot be copied. This is a wonderful story I'll tell you in the next slide. But they exist in the so-called superposition and entangled states. Actually, my Danish colleagues and I had to invent the name entanglement in Danish because 15 years ago there was no such a notion. Entanglement, in fact, is the English equivalent of the German term that Heisenberg and Schrödinger used. So in Danish, correct me if I'm wrong, it sounds sammenfiltring. Say it again? Mange tak. So because of this, we now have quantum information science, and quantum teleportation is a little block in this quantum information science. And thanks to this, in principle, there are ideas of quantum computers, and we can talk about it at the bar. They will not replace your laptops, but they will perform certain operations infinitely faster than any good laptop can do. Here is something that you would really love. No hackers, no interruption of your services, no stealing of your bank accounts. Quantum mechanics promises absolute security of communication. Your communication with me over internet cannot be intercepted without being noticed. In theory. And now this quantum teleportation of objects, or at least of their quantum states. So let's get back to that. Yeah. So this is why I'm here, right? This is why you came. Because either you saw the movie or you heard about it. The maps got it. Now, the bad news is that we don't know how to transform matter into light and back. And we know for fact that no sensible thing, and I can explain what it is, can travel faster than light or even as fast as light unless it has zero mass. Photons, the particles of light, they can travel with the speed of light because they have no mass. None of us can. So transforming matter into light and sending this thing like, you know, this beam Scotty, doesn't work. So what do we want? If the matter cannot be teleported, then what do we want to transmit? And this is this $100,000 question. Information. Imagine that I want to teleport you to somewhere else. All I need to do is to have on this other place a pile of material. I usually say a pile of garbage, but let's say a pile of material, which is enough to build you. Then all I need to do is to send instructions. It is complicated, sure, but in principle it should be possible, right? So I'll send instructions, and then they just, you know, they put you together with kind of some accuracy. No. This is not possible. And it's not possible because I just told you that those electrons, you cannot measure the position and the momentum of those electrons, let alone all your beautiful and complex structure. How many electrons do you have? Plenty. If you cannot completely characterize even one of them, forget about, you know, teleporting me or even you, a much more complex object. So, no way. What shall we do? And here we use this trick of quantum teleportation. We don't send what we call classical bits. We send this quantum information. And at that point, I think we have exhausted more or less the absolutely popular part of the talk. We will have then to go into some domain which is a little bit tricky and a little bit mathematical. And for all that, we still have about 25 minutes. Okay, so I told you that we cannot learn everything about things, and one of the manifestations of that is you cannot perfectly clone things. So we all know this wonderful Dolly the sheep, right? So it's got, you know, some DNA molecules inside, and the DNA molecules are built of electrons. So, yeah, no problem. This is all classical information. The DNA structure is written on a piece of paper. All those, you know, C's and O's and N's. This is all complex but classical known information. You can write it in your computer, you can copy it, you can put it into another dog. However, as we already discussed, you cannot learn everything about small particles, and even if the objects are big, you cannot learn everything. Like with me, you cannot exactly know my position, but the uncertainty of my position is 1 billion times smaller than the thickness of my hair, so who cares? With other systems, those uncertainties can be important, and I will present you with such systems. So, the funny thing is that you cannot take this Captain Kirk, or whoever was teleported, and just create an exact copy on another location. It's not possible. There is a specific theorem which is called a non-cloning theorem. Another good subject for the discussion by the bar. What is non-cloning theorem, dear? And the non-cloning theorem suggests that there is no way you can copy exactly an unknown quantum object. And I'll give you an example. Our object will be simple. Yeah. So here is a wrong but very intuitive example. So we have a magician here, and this magician wants to measure a position and the velocity of a little particle. So how do we do it? Well, we send light. We send light and we look at it. But what does it mean? It means that we send this photon, a particle of light. Oops, sorry, back. So I sent a photon, and this photon, it's like, you know, it's like 2 billiard balls. It got scattered from one another. So I've got a photon to look, but to look at what? This photon tells me about where this particle was, not where it is. And this is an absolutely general rule. As soon as you look at something, you partially destroy it. As soon as you raise your child, you partially pamper it, and, you know, as soon as you meet a guy, you partially destroy it. And so on and so forth. You name your own example. So you cannot live in this world without leaving a footprint. And even when you look at something, you are leaving a footprint. Well, actually, no. No, what I'm trying to say is that it's not when you look, it's when you can see. That's the difference, right? When it would be completely dark here, I wouldn't be able to see you guys. But that means that there will be no photons to be scattered of you and to spoil your otherwise peaceful kind of environment. Okay. Another example. Another example. This is actually arguably the most famous experiment in history of science. It's called the Young is a man, double slit experiment. So here we have a source of light. And here we have a screen with 2 slits. And we send light through this screen. Let's look on the right. Imagine that it's not light, but rather a source of waves. You go to the sea, in summer of course, not now, and you take a little stick and you try to make waves. And then you build a little screen with 2 holes. And what happens is that waves go, 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 and then they go through those 2 little slits. And then now you have 2 waves, one wave going from here and another wave going from here. And there is an interference. And this interference leads to the maximum here and minima in between. You've all seen boats going down the river. They leave behind themselves the wave. And this wave is kind of, it's traveling and it's got a node and an antinode, right? And this thing is actually a result of more complex interference. But now what we're trying to do is we're trying to attenuate this source of light to the extent that it emits 1 photon at a time. This source of light, well, for instance, this source of light. This source of light emits about 10 to 15 photons per second. Okay, so 10 to 15, that will be 1,000 of millions, or 10 to the 9, 10 to the 6, a million billions, something like that, a lot. But still, I can attenuate it so that it will emit 1 photon at a time. How would I know? I can put a detector, and we now have detectors which will just click, photon, click, another photon. So it looks like, billiard balls. However, if you send those photons one by one, and you think that some of them go through this hole, and some of them go through this hole, what should you see? Well, you should see kind of, an even distribution of the photons which are here. Or maybe, maybe you should have a maximum here, a maximum here. What you see in reality is as you send more and more of them, they tend to cluster in particular areas, here, here, here. And if you send 10,000 of them, they will be maxima, minima, maxima, minima. So each photon, being a particle, somehow goes through both slits together. So it's a particle and it's a wave at the same time. It is another example of the fact that we cannot learn everything about the world around us. There is this dualism, and this is what Bohr called Complementarity Principle. Now, if you want to cheat your nature, and you put a little guy here, so those 2 guys, they seriously disputed the situation. And as of today, Bohr is considered to be more right than Einstein, but we shall see. If you want to put here a little guy who will actually quietly sit here and watch, does the photon go through this hole or through that one? Well, it's hard to put a little person there, but there are experiments which tried that. Let's just sneak and see what happens. Which way does this photon go? As soon as you try to do it, the interference picture disappears. So either you know which slot this photon went through, or you have the interference picture. Either it's a particle, or it's a wave, or if you don't look, it's all together. So this is another presentation, and at the first glance, it has nothing to do with teleportation, am I right? Why did you come here? Why are you listening to all this stuff? Well, because my message today is not only about teleportation, about this in principle impossibility, in principle limitations of our knowledge, which are very, very specific. And I think they are remarkable. I also think that they're crazy. And maybe there is deeper theory than quantum mechanics, quantum physics, which we still don't know. Some people think that way. Yes. Why don't we skip this? So, to get a little bit closer to the teleportation experiment, I need to get back to my spins. And the spin can be considered as a quantum coin. So, imagine a coin which is spinning in the middle of this room in all directions, kind of spinning. And then I take this coin and I slap it across the floor, on the floor. It's either heads or tails. I can do the same thing against this wall, heads or tails, or against this wall, heads or tails. So those three results will be called X, Y, and Z projections. Come on, everybody here went to school. Right? You remember those wonderful days? And X, Y, Z, right? This was this teacher. Okay, Jens, come forward. Tell us what the vector is. No? Well, I don't know. Anyway, so here are the projections. And the story is that every normal coin will actually at every moment of time be oriented in a specific way. Either heads this way or heads that way or a little bit at an angle. A quantum coin, a quantum spin does not have any orientation. It's unknown. And it's not because we are bad physicists. It's because nature is built that way. And so the coin can be in superposition of heads and tails. And now if I want to teleport a state of this coin, how can I do it if I don't know whether it's looking, you know, spin up, as I call it, or spin down? It can be like a little magnet, right? Either south up or north up, like this or like that. So you can also assign to it the information content. Let's call the heads 0 and the tails 1. Or south up, spin up 0 and spin down 1. So a particle can be in a superposition of those two states. And my goal is to teleport this state of a particle, a superposition, which I cannot measure. Yes. Now, this is a photograph of the real thing. So it's a little glass cell, about an inch, cubic inch, and there is gas inside. And what you see here is this gas is glowing. The color are artificial, but there is gas and it's glowing. And it's the quantum state of this gas that I will be teleporting. So I'll show you the experiment a little bit later, but just kind of to get you completely disillusioned. The thing which is teleported is a quantum state of all those spins from one of those cells to the other one. They are at a distance of half a meter. They could just as well be at a distance of a kilometer. I wouldn't care. I mean, the lab has a certain size. It doesn't matter because teleportation is accomplished by sending light. So